All right, welcome back to Cognitive Psychology. This is week 16, class number 1, where we're going to finish up our look at chapter 13, Judgment, Decisions, and Reasoning. And actuality, this is where we finish up the course. So this is the last day of classes for this entire semester, where we're going to wrap up our final look at judgments and how it is that we make decisions. So thank you so much for joining me on this, the 9th class of the face-to-face shutdown. And before we jump into the final part of cognitive psychology, just a few words about the upcoming final exam. So once again, this is going to be a little bit different than what we were doing in the first half of the semester, considering that we are not able to meet face-to-face at this time. So because of that, this is going to be another take-home exam. So much like exam number 3, it's going to be available in Canvas May 7th, starting at midnight. So that is the date of the originally scheduled exam. So it'll be available in Canvas on May 7th at midnight. At 1 minute after midnight, and then it's going to be due May 7th by midnight. So you have 24 hours within which to complete this final exam. The chapters that it's going to cover and the lectures that it's going to cover and the Coglabs that it's going to cover are everything that we covered since exam number 3. So that includes chapter 11 on language, chapter 12 on problem solving, and now chapter 13 on judgments, decision, and reasoning. So the final exam is not cumulative. It's just on what we've covered since exam number 3. The Coglabs that we're going to cover are the 3 that we have looked at since exam 3, categorical perception, identification, the weights and selection task, and then today's Coglab, which is the Monty Hall problem. And the lectures that we will be covering in the exam are all of the lectures since exam number 3. So the language lecture, the 2 on problem solving and creativity, and then the 4 on judgment, decisions, and reasoning. So that final exam is going to maintain the format that we've seen so far. So it'll be done through Canvas, and it will still be multiple choice. There will still be 2 sections. Section number 1 is going to cover materials from the readings that were not covered in class. Section number 2 is going to cover materials from the readings that we do cover in class, anything extra that's covered in the lectures, as well as the Coglabs. Because of this different focus, section number 1 will be 33% of your score, and section number 2 will be 66% of your score for the final exam. So again, section number 1, readings not covered in class. Because of that, it will be recognition type questions only, whereas section number 2 will be the readings that we do cover in class, topics that we covered in class during the lectures, in addition to the Coglabs. So it will include recognition type questions as well as application questions. All right, so that's the final exam. So again, May 7th, you have the entire day to complete it. There's no time limit on completing the exam. Open book because of the face-to-face shutdown. So make sure that you, at some point, log into Canvas on that day and complete your final exam. All right, now in terms of what we're going to be doing today, we're going to end this semester and end our look at cognitive psychology with a look at game theory. So game theory is a part of judgment and decision making, but it's a very special sort of twist on it, and we'll see exactly what we're talking about in just a moment. We are then going to take a look at the complexities of game theory by revisiting the Pirate Booty Challenge, but with one little interesting twist that's going to change it from what we had before, which was not game theory, to what we have now, which is going to be game theory. We're then going to take a look at another example of a game, the 2/3 of the average game, that can be used to measure how rational people really are. Again, remember that distinction between what you should do, the prescriptive reasoning, and what you actually do, the descriptive reasoning. This is one way of measuring potentially that difference. And then we're going to finish with a look at the Monty Hall problem and just a little bonus content on Marilyn Savant and the confirmation bias as it applies to sexism that we introduced last time. We touched a little bit on that confirmation bias. Today we're going to see a real world example of where confirmation bias led things to get a little bit uglier than they needed to be. All right, so game theory. Game theory is a subcategory of decision theory, and it's the subcategory that applies when your success in making a choice depends upon the choices of others. So this is a special subset of decision theory where it's not just you independently acting, but somebody else is acting as well. And more importantly, their actions factor into whether or not you make the correct choice. So when you think of a typical game, that's part of the game play. If you're playing against an opponent, what you do is important, but also what they decide to do is also important. So that's the key characteristic of games, and that's where we get into the decision theory part that is known as game theory. So far, we've seen a few things that are not game theory. So, for example, the Tower of Hanoi, the version that we looked at was the simple single-player version. That did not depend on another individual. You sat there by yourself and played the Tower of Hanoi. Sure, you had to do decisions along the way. Sure, it required reasoning and navigation of a problem space, but it was not dependent upon the actions of anybody else, so it is not part of game theory. The Orcs and Hobbit problem, very interesting riddle. As we saw, illustrated our aversion to backwards movement in the game space, that backwards avoidance heuristic. But once again, it did not depend upon the decisions of anybody else but yourself. So once again, that is part of decision theory, but not part, and reasoning, but not part of game theory. And then today we're going to see another example of reasoning that is also not a part of the game theory, or not a part of game theory, and that's the Monty Hall problem. And once again, that simply has to do with your decision, and there's no impact by anybody else making a choice on whether or not you're successful or whether you are. So those are examples that we've seen so far that are not part of game theory. So what is part of game theory? Well, one that we've seen that is part of game theory is the dollar auction. So the dollar auction is a part of game theory because how successful you are at the dollar auction depends upon what other people do. And the easiest example of that is that if you bid $5 and nobody else bids anything, if they make the choice of not bidding anything once you bid $5, then you will be incredibly successful with your decision to bid $5. On the other hand, if you bid $5 and then somebody else bids $10 on top of you, you will be less successful. So your success in the dollar auction depends upon what you do and also depends upon what other people do. So to be successful in the dollar auction, you not only have to consider your actions, you have to consider what other people might do as well. And we're going to see this in the Pirate Booty Challenge Revisited version. That's also a part of game theory because we're going to make it where you interact with other real-world pirates and not the hypothetical rational pirates that we were dealing with before. So it goes from being a mathematical logic problem to being a psychology problem about how you interact with other people. And then typically other examples include what we normally think of as games. So if you ever played a board game with other people, your success usually depends upon the decisions of others. In Monopoly, your success depends upon whether people build hotels and buy properties. In Risk, your success depends upon how many units do people put on their different countries. In poker, your success depends upon how the other person is playing. If they fold, you win. If they go all in, you might have a different outcome. Your success depends not just on what you're doing, but also on what your opponent is doing as well. So just as we had prescriptive reasoning and descriptive reasoning, just as we had prescriptive decision and descriptive decision theory, we also have prescriptive game theory and descriptive game theory. So the prescriptive game theory is what strategies humans should use. That is, what is the correct thing for them to do in that game? What is the best strategy to use in a particular game? And that is based on philosophy, that is based on logic, that is based on mathematics, that is based on an analysis of the game. So for example, in Monopoly, there is a strategy that has been identified as one of the best strategies to use in that game, which is to never build hotels, but simply to have as many houses on your properties as possible. You can Google it if you're interested. But that is a prescriptive game theory. That is people proposing this is how you should play. A descriptive game theory, on the other hand, are the strategies that we actually use to play the game. What are the actual behaviors that we use? And as you might have read in your textbook, how we operate is based on our psychological abilities. So one of the most interesting sort of analyses or findings in game theory was that when adults play a game, they tend to weigh the different outcomes, like the positive outcomes and the negative outcomes. They tend to weigh those. When children play a game, they tend to only envision the positive outcomes. So they will make their decisions based on what is the best thing that could possibly happen. And that's why children play games differently than adults. All right, so now that we have the idea of prescriptive game theory, how should we play the game to be maximally effective, versus descriptive game theory, how do we actually play the game, we are going to revisit the Pirate Booty Challenge. So before we get into the new version, let's revisit the old version to see what was the descriptive decision making that took place in the Pirate Booty Challenge. So we've already analyzed the prescriptive decision making for this Pirate Booty Challenge. So if you don't remember that, or if you haven't seen the Pirate Booty Challenge yet, I recommend you go back to the previous lecture, watch the video on the Pirate Booty Challenge, and see what that correct answer was. So given that we've already talked about the prescriptive decision theory, what was the actual descriptive decision making that took place? So this is data from a previous class, and what I did is I collected their results. I collected their allocations, and I graphed how much did they keep for themselves. How much did they keep of the 100 gold coins for themselves? So they were Pirate A. How many of the gold coins did they keep for themselves? And this was everybody that survived. So if you didn't survive, you didn't make it into the data set. This is everybody that survived as Pirate A. So on the bottom there on the x-axis, you can see the Pirate A allocation. So whether they assigned themselves 0 to 4 coins, whether they assigned themselves 10 to 14 coins, 20 to 24 coins, 30 to 34 coins. So it is going up in kind of 4 coin allocations. So 0 to 4, 5 to 9, 10 to 14, 15 to 19 across the x-axis. And then we have the frequency on the y-axis, and this is how many students came up with that solution. So I've been collecting this data. I think this was across a couple of classes. But basically, the higher the bar, the more people chose to do that solution. So what were our results? Well, these are the results right there. So as you can see, most Pirate A's, most students gave themselves 30 to 34 gold coins. So this is the idea, again, based on the heuristic that they're in charge. So they should get more than average. They should get more than what everybody else is getting. So they do that by giving themselves 30 to 34 coins. And then everybody else gets a different allocation. We can also see that the second most common allocation was to give themselves 20 coins. And these were the solutions where they decided on the heuristic that everybody should be treated equally. So they were just going to give 20 coins to every single pirate. Everybody gets 20. We divide it all evenly. And that is using your real world experience, using that, again, that strategy of using that real world knowledge to basically say, we're all in this together. So let's split it up the way that it should be. Now notice that we have about 40-ish data points here. Notice that we only have one person that came up with the prescriptive solution. We only have one person that did the allocation of 98 coins, 0, 1 coin, 0 coins, 1 coin for the 5 pirates. So there's your prescriptive solution. We only had one person. And as a cognitive psychologist, you would try to determine why is it that these other solutions were made. So why is it that most people decided to give themselves 30 coins out of the 100, followed by people giving themselves 20 of the coins, splitting it up all equally, followed by people giving themselves 40 coins. So were the people giving themselves 40 coins slightly more aggressive? Are they slightly more into seniority, slightly more authoritative? What was the outside experience that they were bringing to their solutions? Those are all the sort of follow-up questions that we would have with this type of result. All right, so on that note, we have a very special guest with us today that I would like to introduce right now. So as part of Take Your Child to Work Day, I know that was last week, but better late than never. As part of Take Your Child to Work Day, I would like to now introduce my daughter. Her name is Isabella. So just a little bit of background on Isabella. She is a swimmer. She swims for the YMCA Stingrays. Not only is she a swimmer, but she is the Indiana YMCA state champion from 2019. So that's her winning her state championship in her age group. And that is her posing with her state championship in her age group. So very accomplished swimmer. Also a budding artist, so she actually has a book that is available for purchase on Amazon, as well as working on her own comic book on a character she calls Emily Rocket. And here you can see Emily Rocket trying her best to work on her mind, trying her best to work on her cognitive abilities, and struggling a little bit with exactly putting a puzzle together. But again, this is all part of Isabella's artistic talents. So without further ado, I would like to turn this over to Isabella, and she is going to take us through the revisited portion of the Pirate Booty Challenge.
Hello there. So we are going to be doing the Pirate Booty Challenge Revisited. Now, there are 5 rational pirates, A, B, C, D, and E. They are doing their end-of-the-year distributions. They have found 10 100 gold coin treasures. They must decide how to distribute each treasure. The pirates have a strict order of seniority. A is superior to B, who is superior to C, who is superior to D, who is superior to E. Now let's move on. The pirate world's rules of distribution are thus. For each individual treasure, the most senior pirate should propose a distribution of coins. The pirates, including the proposer, then vote on whether to accept this distribution. If the proposed allocation is approved by a majority or a tie vote, it happens. If not, the treasure is thrown overboard from the pirate ship. The most senior pirate makes a new proposal for the next treasure of 100 gold coins. This continues until all 100 gold coin treasures have either been allocated or thrown overboard. Pirates base their decision on 2 factors. Each pirate wants to maximize the number of gold coins they receive by the end of all 10 allocations. Pirates base their decisions on 2 factors. All things being equal, each pirate tries to minimize the number of gold coins that the other pirates receive. Your challenge: try to maximize your allocation of gold coins. In the single treasure version, final allocation. Pirate E gets 1 coin, Pirate D gets 0 coins, Pirate C gets 1 coin, Pirate B gets 0 coins, and finally, Pirate A gets 98 coins. If this strategy is applied to the 10 treasure version, final allocation, Pirate E gets 10 coins, Pirate D gets 0 coins, Pirate C gets 10 coins, Pirate B gets 0 coins, and Pirate A gets 980 coins. But wait! If Pirate E votes against the single what if Pirate E votes against the single treasure allocation? Final allocation. Pirate E gets 0 coins, Pirate D gets 0 coins, Pirate C gets 0 coins, Pirate B gets 0 coins, and Pirate A gets 0 coins. Not so much fun. If Pirate E follows his strategy, Pirate A must change her strategy. Pirate A's new strategy. Pirate E gets 2 coins, Pirate D gets 0 coins, Pirate C gets 1 coin, Pirate B gets 0 coins, and Pirate A herself gets 97 coins. If Pirate E follows his strategy, Pirate A must change her strategy. Again, final allocation. Pirate E gets 18 coins, Pirate D gets 0 coins, Pirate C gets 9 coins, Pirate B gets 0 coins, and Pirate A gets 873 coins. But wait! But what if Pirate E votes against Pirate A's new strategy? Final allocation. Pirate E gets 0 coins. Pirate D gets 0 coins. Pirate C gets 0 coins. Pirate B gets 0 coins. And Pirate A gets 0 coins. Nobody got any coins. If Pirate E follows his new strategy, Pirate A must change her new strategy. Again. Pirate A's new strategy. Pirate E gets 3 coins. Pirate D gets 0 coins. Pirate C gets 1 coin. Pirate B gets 0 coins. And Pirate A gets 96 coins. If Pirate E follows his new strategy, Pirate A must change her new strategy. Final allocation. Pirate E gets 24 coins. Pirate D gets 0 coins. Pirate C gets 8 coins. Pirate B gets 0 coins. And Pirate A gets 768 coins. But wait! What if Pirate E votes against Pirate A's new strategy? And what are Pirates B, C, and D going to do? Game strategies can get quite complex. Your challenge tries to maximize your allocation of gold coins. Then why don't you go ahead, pause the video, and try that right now.
All right, so thank you so much, Isabella, for that. She's going to come back and join us again on the Monty Hall problem. But for now, right now, let's take a little deeper dive into game theory. So just keep in mind what your final allocation would have been. What would your best guess in terms of how much could you allocate as Pirate A? What was that number, and what would that be after 10 allocations? And again, now that you had to take into account not just what you would do, but what your fellow pirates would do, not just how you want to allocate things, but how they would vote, because their voting is now not fixed, you can see how it gets much more complicated to determine what is the prescriptive game theory. So the descriptive game theory we could get just by running this simulation, and I've done this in class before, just running the simulation and see how it turns out. And just to kind of let you in on a little bit of the results, treasures do get thrown overboard. So treasures do get voted down and thrown overboard as a signal to the lead pirate that they better change their allocation. So again, it's this sort of like, what's the other person going to do? How is my decision going to be met by their decision? And that affects the strategy and the success of the overall pirates. And that is part of game theory. So once again, we have that prescriptive game theory. What should you do? What is the best sort of strategy? And then we have the descriptive game theory. What do we actually do? How do humans actually play this game? So in terms of prescriptive game theory, I want to give you one example of a prescriptive game theory that has been worked out, and that has to do with X's and O's, or noughts and crosses if you're from across the pond. So X's and O's, this is a game that we've all played before. This is a game that we grew up playing as children. And this is a game that you probably do not play anymore. I mean, you might play with like younger members of your family, with like your nieces and your nephews, but you probably don't sit down with your similarly aged friends, with your adult friends, and sit down on a Friday night for a rousing game of tic-tac-toe. And one of the reasons for that is because tic-tac-toe, whether you know it or not, you have developed the prescriptive game theory for tic-tac-toe. You have in your mind represented the correct way to play tic-tac-toe, and that is why you will always end up with a tie. If you play against another person with that prescriptive game theory, you will end up with a tie in tic-tac-toe, and that's why we no longer play it, because the ending is now uninteresting. So what is this prescriptive game theory? How can we conceptualize or visualize this prescriptive game theory? Well, here we have an example of a visual version of the prescriptive game theory. So this is your strategy for winning X's and O's. And this is basically your first move followed by every other move. So this is if you're playing first. So if you're playing first, the best move that you can do, the best strategy is to go into one of the corners. Now, because X's and O's is symmetrical, it doesn't matter if it's your top left, top right, bottom right. It's the same game theory. You can just spin the board for wherever you start. So let's just assume that they're all the same, and we're going to talk as if we start in the upper left. Once you start in the upper left, your opponent is going to have certain choices in terms of where they go. And you can see that each of the squares in this game theory representation of the game space shows you where the next O goes. So if you take a look at the top row middle square, you can see that the O, that's for when the O is placed into the top row in the middle square. If you take a look at the top row on the right side, you can see that the O has been placed into the top right corner. If you take a look at the bottom left corner, you can see that that black O has been placed into the bottom left corner. So this represents your opponent's next move. So where does your opponent move? So let's say that your opponent moves to the bottom center square, and they put an O right there. That then transports you into that level of this game space. So let's zoom in on that. And you can see now that your best move is that red X. So the X is always your next move. So if your opponent puts the O in the bottom middle square, you want to put the X into the top left. And then if your opponent follows that up by blocking your move, by putting their O into the top center, you then jump into that portion of the game square, of the game space, and your next move is to go center. So if you go center, then if your opponent puts their O into that bottom left, well, then you put your X into the bottom right and you win the game. And you can see that at that point, there's nowhere that the O can go that does not allow you to win the game. So that is a portion of the game strategy. And we actually have that entire strategy represented in our mind so that regardless of where the O is placed, we know the moves in order to win at tic-tac-toe. And again, that is why we give up playing tic-tac-toe. Now, games that people do play are the games where we don't have the entire problem space represented in our mind. So chess is a prime example of that, where the first 10 moves in chess, I think there's something like more atoms in the world, in the universe, than there is more opening. There's more, let me try that again. There is more 10 move opening sequences in chess than there are atoms in the universe. It's something like that. Bottom point is, don't quote me on that. I'm probably wrong. But the main point is that there's an astronomical game space for chess. And that's why chess is very, very difficult to master. That's why people don't give up playing chess. That's why nobody has ever said, you know what? Every single time I play chess against my friend, it ends in a draw. It's not fun anymore. There's nothing new anymore. We keep doing the same moves over and over and over again. You don't say that because you don't have the game space for chess figured out completely. You do have it for tic-tac-toe. You have the prescriptive game theory for tic-tac-toe in your mind. And that's why you don't play it anymore, because it's no longer interesting. That navigating of the game space is what makes games challenging and fun. All right, so let's do another challenge here. We're going to check out the Are People Rational challenge. So this is not game theory, but kind of game theory, and I'll explain why in just a moment. So guess 2/3 of the average is the game that we're going to play. And what you're going to do here is you're going to guess a number between 0 and 100. So any number you want between 0 and 100. It's going to be a whole number, but any number you want between 0 and 100. And the winner, imagine that you're playing this against the rest of the class. The winner is going to be the person whose guess is closest to 2/3 of the average guess. So that's the key there. What's going to happen is that at the end of the guesses, the games master would collect all the guesses, total them all up, take the average of those guesses, multiply it by 2 and divide it by 3, and whatever number ended up, that's the target number. And whoever's guess was closest to that target number, they're the winner of this challenge. So for example, if we were playing this with 5 players and player A guessed 50, player B guessed 47, player C said 76, player D said 55, and player E said 7, the average of all those guesses is 47. So 2/3 of that average is 31.3, and the winner in this case would be player B. So let's try that with an in-class demonstration, or in this case, sitting at home watching this video demonstration. So what I would like you to do is I would like to give your best guess for the 2/3 of the average of the guesses. So much like this example just showed here, if you were playing this against your fellow classmates at IUSB, if we were able to do this live, what would you guess? What would be your best guess for 2/3 of the average of everybody's guesses? So give that a moment. Take a moment to think about it. Try to rationalize what you would do. And because this is game theory, try to rationalize what other people will do, because it depends, your success depends on their success. And see if you can figure out, number one, what the prescriptive solution is. And then number two, give us your best descriptive solution. Pause the video at this point, come up with those two guesses. Prescriptive guess, what would the rational thing be if everybody was rational? And then your descriptive guess, what do you think is the actual best answer? And come back once you have those numbers written down. All right, so do you got your numbers ready? Do you have your prescriptive solution? And do you have your descriptive solution? Well, let's take a look at the prescriptive solution first. What is the rational strategy for this particular game? And the easiest way to identify what the rational strategy is try to do an iterated solution. Go kind of step by step working through this game to see what a rational player would do. And again, this is assuming they're also playing against other rational players. So if your maximum guess is 100, right? You got to guess a number between 0 and 100. If the maximum guess is 100, then guesses between 67 to 100, those are actually impossible. Because even if everybody guessed 100, if everybody misunderstood the game and said, oh, I'm just supposed to guess 100, I'll just write 100 down. If they all wrote 100, then the games master took 2/3 of 100, it would be 66.7. So guesses between 67 to 100, those are impossible. You actually can't get those numbers. You can't get that high of a 2/3 of the average in this situation. So what that means is that if you're a rational person, if you thought this through, you wouldn't guess higher than 66. So the maximum guess for a rational person is 66. But that's only the first part of this solution. So if the maximum guess for a rational person is 66, and everybody in this situation is rational, that means that guesses between 44 to 66 also become not rational. So they're not impossible, but they're not rational. Because if everybody knows the maximum you can guess is 66, well then 45 to 66 is out of the question, because 2/3 of that rational maximum guess of 66 is only 44.7. So that disqualifies anybody playing against other rational individuals that guesses between 44 and 66. So what does that mean? Well, that means that if you're rational and you're playing against other rational people, the maximum guess for a rational person is 44. We go one more step. If the maximum guess for a rational person is 44, and that's how high anybody who's rational would go, well then guesses between 30 to 44 are also not rational. Because once again, 2/3 of 44, 2/3 of that new maximum guess is going to be 23.9. So the maximum guess for a rational person is going to be 29. And then we keep going. And if the rational guess for if the maximum guess for a rational person is 29, and you compete against other rational people, then you take 2/3 of that, and then after that you take 2/3 of that, and then after that you take 2/3 of that. And the process continues until you come to the solution that the prescriptive strategy, if you're playing against other rational individuals, is to guess 0. The rational person will guess 0. That is the best solution for this particular game. So did you guess 0 for your prescriptive solution? Did you work it through and say, you know what, if I'm rational and everybody else is rational, 0 is the only number that we could possibly guess. 0 would give you the best chance of winning. So did anybody get 0? And if you didn't, what was your descriptive solution? Because there is a little hole to this argument that allows for psychology to come in and allows for game theory to come in. Because this solution is almost like the first version of the Pirate Booty Challenge, where you assume that everybody else is rational. You assume that the other pirates are rational. You assume that they're not going to want to throw a treasure chest overboard at any point in time, right? So if you assume that everybody else is rational, then the best guess is 0. But notice that that might not be the right assumption. That might not be a prescriptive game solution, because if other people aren't rational, then this does not become the best way to do this. So 0 is the best guess, and that assumes that everybody else is rational. That assumes that your play and everybody else's play in this game is going to be rational. But guesses above 0 could actually be rational. They could actually be the prescriptive guess if you factor in that other people are not rational, that other players have not thought it through. So this is a possibility, and this is another wrinkle in game theory, where you can very easily figure out what is the right thing to do if everybody else did the right thing. But in order to have that prescriptive strategy, you then have to try to figure out, well, what is the best thing to do if other people act the way that humans act? So what is the prescriptive decision if other people are doing the descriptive decision? And again, you can see how complicated game theory can get. So either players are irrational and they cannot determine 0 as their best strategy. That's one reason why you might have guessed higher than 0. You just couldn't figure out the prescriptive solution. Or on the other hand, you might have assumed that other players are going to be irrational as well, in which case you could determine that 0 would be the best strategy if you were playing against other rational individuals, but you're not playing against other rational individuals. Therefore, 0 is no longer the best strategy. And we got a little bonus conditional syllogism in there just for you. So 0 might no longer be the best strategy. So what is the best strategy? Well, this is one of those instances where, again, it's very complicated and you just have to try to run the data. You just have to try to run the experiment and see what happens. And a Danish newspaper, the Politiken, did this, and they had a contest. They had a contest where people sent in their best 2/3 of the average guesses. They received over 19,000 entries, and the winning guess, they allowed it to go to decimals, the winning guess was 21.6. So you can see in this case that they did figure out, most of the people figured out that, you know what, we kind of have to go a little bit low, but not all the way down to 0. And again, there's two possible answers for this. It could be both and, that people just couldn't figure out what the prescriptive solution was, and or they also knew that people that they were playing against wouldn't figure out the prescriptive solution, meaning that it becomes the not optimal solution, and you have to go with another example. All right, so what we're going to do right now is I'm going to welcome back Isabella, and she is going to take us through the Monty Hall problem with a little bit of bonus confirmation bias stuff on Marilyn von Savant. So without further ado, I'd like to welcome back Isabella to take us through our final COG Lab.
Coglab Monty Hall problem. The Monty Hall problem. Named for the original host of Let's Make a Deal. Suppose you're on a game show and you're given the choice of, 3 doors. Behind one door is a car. Yes! Behind the others, goats. But I want to keep the goats. You pick a door, say number 1, and the host knows what's behind the doors. Opens another door and say number 3, which has a goat. He then says to you, do you want to pick door number 2? Is it your advantage to switch your choice? Whisk Taker and Voss Savant. This is Marilyn Voss Savant, known for having the highest record IQ, Guinness Books of Records. Now, here is Voss Savant and the Meaführer on Wikipedia, and we are going to take a little sneak peek at one of the parts of the Wikipedia page. Savant wrote in her first column on the Monty Hall problem that the players to switch, saying the first door has a 1 in 3 chance of winning. Hence, the second door offered to switch has a 2 in 3 chance, as the host always opens a losing door on purpose. She went to explain her answer by asking the reader to visualize the case where there are 1,000,000 doors, and the player picks number 1. Then the host, who knows what's behind the doors, will always avoid the one with the prize, opening all remaining doors except door 777. Her conclusion: you would switch that door pretty fast, wouldn't you? In response to her answer, Savant reached thousands of letters from her readers, many with PhDs telling her that she was wrong. Of the letters from the general public, 92% were against her answer, and the letters from universities, 65% were against her answer. Wow. Overall, 9 out of 10 readers completely disagreed with her answer. During 1990 to 1991, 3 more of her columns in the Parade magazine were devoted to her debate with her readers, and the debate was also replayed with other venues and reported on in major newspapers such as the New York Times. This is a letter from Scott Smith, PhD, from the University of Florida. You blew it, and you blew it big! Since you seem to have difficulty grasping the basic principle at work here, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. It's enough mathematical literacy in this country, and we do not need the world's highest IQ propagating more. Shame. That is very insulting. Just so you know, never say that to anyone. Now this is Charles Reed, PhD, from the University of Florida. May I suggest that you obtain and refer to a standard textbook on probability before you try to answer a question of this type again? Nah, man. That's just nah. Now this is W. Robert Smith, PhD, Georgia State University. I am sure you will receive many letters on this topic from high school and college students. Perhaps you should keep a few addresses for help with future columns. Basically, what he's saying, college and high school students are smarter than you, which is totally not true. This is E. Ray Bobo, PhD, from Georgetown University. You are utterly incorrect about the game show question, and I hope this controversy will call some public attention to the serious national crisis in mathematical education. If you can admit your error, you will have contributed constructively toward the solution of a deplorable situation. How many mathematicians are needed to get to change your mind? Okay, how many insults are going to be here? Now, Ever Harmon, PhD, from the U.S. Army Research Institute. You made a mistake, but look at the positive side. If all those PhDs were wrong, the country would be in some very serious trouble. They are wrong. Your country is in serious trouble. Gary Clarks, Western State College. You are the goat. Don Edwards, Sun River Origin. Maybe women look at math problems differently than men. Nah, man. Nah. Thank you guys so much for joining me. I hope you have a wonderful day. My part is done, and now on to
Dr. Yurichevi.
part. Bye-bye.
All right, so you can see there confirmation bias, people acting very negatively toward Marilyn von Savant's answer to this question. And Whether they got it right or wrong, that's not the sort of confirmation bias here. But what is that confirmation bias? Well, they were looking for evidence to confirm their own beliefs. And the belief that fueled a lot of this very negative reactions to her solution is the sexist belief that women just can't do math. So if you take a look at the sort of spin that this all had, if we just take a look at this last one, maybe women look at math problems differently than men. Well, Don Edwards from Sun River, Oregon, that's a belief that they had. That was a belief that they had. So rather than taking the evidence and saying, you know what, let me think about this. She has the highest IQ ever measured, ever recorded. Maybe I should take that into consideration and take a look at what her argument. They said, you know what, no, I'm going to look for any reason why I can confirm my own bias that maybe women look at math problems differently than men. And I'm going to use that to come to the confirmation that, you know what, she has to be wrong. And that's the data that I'm going to preferentially process. All right, so now that we've taken that little detour into confirmation bias, let's finish up with a look at the results for our Monty Hall problem Coglab. So once again, the situation, you're on a game show, you got 3 doors. Behind one of those doors is a goat. Behind another one of those doors is a goat. And behind that final door is a fine automobile. And your job is to try to win that car. And you get to pick one of the doors. And then after you pick the door, the host, who knows where everything is, who knows where the goats in the car is, will reveal one of the goats. And then your choice is, do you switch or do you stay? What is the prescriptive solution to this Monty Hall problem? Is switching going to give you the best chance to succeed, like Marilyn von Savant thought? Or is not switching going to give you the best chance to succeed? Or alternatively, does it not make a difference? Does not switching or switching make absolutely no difference, as many of the responders to Marilyn von Savant's column thought? All right, so what is the solution to this? Well, let's take a look at the COG Lab. This is a Monte Carlo experiment where we just actually ran it. And we actually said, you know what? A lot of people disagree on what the actual numbers are. Let's just run it. So on each trial, you were asked to pick one of 3 doors. You were then shown that the prize was not behind one of the remaining 2 doors. And your task was to simply choose between staying with your original door, a stay response, or picking the other door, that would be a change response. So here we have an example screen grab from this Coglab. So there are your 3 doors. So you would choose the yellow door, and the computer would reveal that there is nothing behind the blue door. And then your choice is to whether you stay with door 1 or whether you change to the unopened door that you haven't selected, door number 3. And in this case, if you stayed, you would have won the prize. And here is another example where you choose the red door, the computer opens the yellow door, and this time, if you switch, you would have won the prize. So should you stay, should you switch, what's the prescriptive game solution? So the independent variable here is the strategy that you employ. Do you stay with your original choice, or do you switch to a different door? One of those has a better outcome than the other one, so let's take a look at what that outcome actually is. So here on the x-axis, we have your success when you stay with the initial door, and you have your success when you switch to the other door. And then on the y-axis, we have the frequency with which those 2 choices occurred. And then you can see there in the legend that the blue bar is the number of times you won with a particular strategy, and the red bar is the number of times you lost with a particular strategy. So let's start with the choice to stay with your initial door. As you can see here, the blue bar is lower than the red bar. So the blue bar is when you win, you stay with the door you originally chose and you win that car. The red bar is where you lose. You stay with your original door and you end up getting the goat. So as you can see here, staying with your initial door is less successful. You get less wins than you do losses. Staying with the initial door, staying with your initial choice, you get fewer successes than you do losses. Now the question is, what happens when you switch? Will the pattern be exactly the same? where we still have fewer wins than we do losses? Or will the pattern reverse, where now switching gives you more wins than losses? As it turns out, Marilyn von Savant was correct. When you switch, you win the car twice as often as you win the goat. So switching to the other door is actually the correct prescriptive solution. You're not going to win every time, but it gives you the best chance of winning. And if we take a look at the percentage of these wins, you can see that staying with the initial door gives you about a 30% chance of winning, whereas switching to the other door gives you a 60-something% chance of winning. So switching to the other door is definitely the right move. It's been shown in this COG Lab where you are more successful when you switch. So it does make a difference. It's not an equal probability that you will win if you switch or if you stay. Switching actually is the better alternative. Switching will lead to more wins if you play in the long run. All right, so one last little send-off before we finish today's class. So Marilyn von Savant, as I mentioned, she's known for having the highest recorded IQ of all time. So this was in the Guinness Book of Records. While they still kept that record, I think they retired that record. And just to kind of give you a little bit of an example of sexism, especially now that people are trying to revert or undo a lot of the kind of sexist attitudes and sexist opinions that have infiltrated our culture, that even if you don't consider yourself sexist, you might still have these kind of tendencies that it is very difficult sometimes to be aware of these biases that we have. And just as a sort of public service announcement, to be a little patient with people that, kind of show these biases, and to know that just because you have the bias does not mean that you're sexist. I wanted to call attention to this article here by Zachary Crockett. And the article here was titled, "The Time Everyone Corrected the World's Smartest Woman." And I just want to kind of draw attention to that, because that title there in and of itself, even though this is an article defending Marilyn von Savant, is actually also showing the bias of either the writer or the editor, because this wasn't the time that everyone corrected the world's smartest woman. This was the time that everybody corrected the world's smartest person. So once again, to give you that kind of like impact, to give it that little bit of extra oomph, they highlighted her as the smartest woman. The implication being that, she was, the implication being that it wouldn't be as smart as the smartest person. So you can see that even when you're trying to be an ally, sometimes those biases can still come in. It's going to take reprogramming. It's going to take rethinking and re-experiencing our cognitive world. And then as we continue to go on and those connections are being made, things will move forward. And that is the trajectory that our society is going in. So have a little patience for people, because again, she had the highest IQ, world's smartest person. And even somebody coming to her defense still emphasized the fact that she was a woman, still showing that bias. All right, so that is it for today. That is it for the semester. So thank you so much for joining me and playing along this entire semester. I hope you learned a lot about how your mind actually works. And once again, this will be the final sign-off. So keep yourself safe, and I hope to see you in another one of my classes soon. And other than that, thank you for joining me, and I'll hopefully see you again.